I'm like so on top of everything, so I'm like, oh, I'm gonna fall behind.
Yeah, right.
And so I already started week 2 or
This is
something.
more than like math.
All I have left in this week is the lab. We fall behind and they were like random muscles and stuff, and you're always like,
Yeah, just
Like figure out like started working on the I got most of the way
I think that was
I was comparing the answers to what she listed. Some of them don't make sense. Where did that go?
she knows more than us. She accidentally like come out. She's like talking about stuff from chapter 9.
Did you finish it in or?
Yeah, because so
Like you have to like read this article thing.
He has it.
Oh, yeah.
I mean, it's not good.
No, inside the actual
Does he have a different Yeah. That's true. So what is it? Yeah, just where's the Yeah, it's only or what? Yeah, they gave me one of those. Yeah, he did. But you like have to watch. I did not keep loading. So like trying to tell us how just only four
Oh, wait. What's up, boss?
recitation.
I think we get the other. It's in there, it's just like, we don't know where the room is proportionate. It's like, oh, well, you're done. Like, I think it was just like, when's the last week? Yeah, or like, in the last week or eight, or in November. I literally, like the last week, biology did that. But, I think it's just, I don't know.
Yeah. They combine them too. Well, it's like the nitro one.
Yeah, that's a bunch of weeks.
Spring and fall.
Were you even doing it?
They're playing metal, I mean, not like burn really fast, like melt first.
Oh, yeah.
Yeah, that's what I was thinking too.
All right, let's go ahead and get started. So take the first minutes of class and see if you can do this practice problem. So picking up from where we left off. So determine the volume of an object that has a mass of 455.6 grams and a density of 19.3 grams per centimeter cubed. See, do we have an answer yet? What did you say? So I have 23.6, thumbs up, thumbs down. Awesome, I see a bunch of thumbs up. And so let's just go over it, just so we're all on the same page. So I like the triangle trick. So we have density equals mass over volume. So density, mass, volume. So it wanted us to find the volume. So if I cover that up, looks like we need to just do mass divided by density. And so once you set up our problem in our dimensional analysis, so divided by density, that means centimeter cubed goes on top, 19.3 grams on bottom, so grams cancels out. And so 1 centimeter cubed, by the way, is also 1 milliliter. And I can also plug that into the calculator. So 455.6 divided by 19.3. All right, excellent. Any questions on density or this before we keep moving on slowly? All right, so let's just finish up the tail end of chapter 1. So the tail end of chapter 1 is just bringing up our units of energy. And so we have our SI units of energy are going to be in joules. And we can relate this to kinetic energy. So we have kinetic energy is 1/2 mv squared. And so do you know what the units are in physics for this? Maybe some of you are in physics. So do you know what physics tends to plug in for mass? You know, it's grams, kilograms. Anybody in physics currently? Physics. Huh? Nice, nice. Yeah, kilograms. And then what do we tend, so this is velocity. What's velocity measured in typically? Meters per second, excellent, so meters per second, and then that's squared. So if we plug that in, and this will give us our units of joules, so this gives us kilograms, meters squared over seconds squared, and that is what a joule is. So if you break that down, so 1 joule is equal to 1 kilogram meter squared second squared. So same thing, just wrote it out different forms so you see it, know it. So that's where those units come from. And if you're taking physics or need to take physics in the future, pay attention to these dimensional analysis rules. They will help you. I swear the only reason I got through physics is unit canceling. And then so we have 2 different forms of energy as well. So this is kinetic energy. And so kinetic energy, just briefly, is energy related to motion. And that can be anything from you walking around, flailing your arms, to also just movement of electrons, so that's also kinetic energy. And then we have potential energy, and so this is just mass times gravitational constant times our height. It gives us potential energy, so this is energy either related to position, as is given by this equation, but then later we'll talk about in chemistry, we're more interested in kind of the potential energy in bonds. So we'll look at chemical bonds and all the energy that's stored in there. And of course, your food, right? Fundamentally, you're breaking down all your food, getting your energy from food. So that's potential energy, and of course, being converted into kinetic energy. And then just some kind of fun facts so we can orient ourselves on what a joule is. And so let's start with a joule. So that 1 joule is the energy it would take to lift 100 grams to a height of 1 meter. So you can kind of, visualize that. How much energy is that? And then comparing, so a BTU, So this is British thermal unit. That's now almost 1,000 joules. 1 calorie, so this is like your nutritional calorie that you would find on your back of the nutritional information. So that's 4,000 joules. So again, kind of putting that in context, like, that's why you have to work out so much, right? To burn off all those calories. And then so average nutritional need, 7 times 10 to the 6 joules, and you can read these for yourself. And then of course all the way up to the energy from the sun that hits the earth in one day is 1.5 times 10 to the 23rd joules. Hence why a lot of people are interested in solar energy, but we won't go down the rabbit hole today of solar energy. And you can see nuclear, also a lot of energy. And on the smaller side, so later we'll also discuss like photons. And so that's going to be 1 individual packet of light. And just for comparison, that's 10 to the negative 19th joules. So a very wide range of things we can look at energetically. And then this is just a basic graph here showing that generally, let's say you start with kinetic, then it's going to be converted to potential, or vice versa. So you can start with no potential energy, and if you do something right, move it to a higher position, so you put work in, now it has potential energy, drops back down, repeats the cycle of converting potential to kinetic energy. And so other things that we should look at as we finish up this chapter. Oh, and then, I was skipping something. So this energy total then, your total energy of a system is just equal to your potential energy plus your kinetic energy. So you can abbreviate it like that. But again, this is just kind of an overview of energy. We'll delve deeper into this in another chapter. All right, so back to doing experiments and kind of how we can quantify, how we can tell whether our data is good or not. And so let's look at these different ways to quantify this. So when we have our set of measurements, let's say you've set up, your apparatus, you've done your measurements, now you're kind of looking at your data. And so there's kind of 2 different ways we can analyze our setup, our experiment, see how things are going. And, this is going to be kind of vague because it depends what you're measuring. But we can either compare our precision. So this means that it refers to the closeness of measured values to one another. And so that means how accurate are we in our setup. So let's say we're trying to measure the speed of light. Right? That's something that's known. And if you look at your setup, first thing you want to see, are my values fairly consistent? So right now you're not evaluating whether they're correct, just are they landing around the right spot? So maybe you're under, but as long as you're consistently under. So the speed of light is 3 times 10 to the 8 meters per second. Well, let's say your setup was a little off, but you consistently got like 2.5 times 10 to the 8 meters per second. I was like, well, at least I know I have some sort of systematic consistent error, and then I have to determine what's wrong, but my precision is correct. If you don't have precision, maybe your numbers are all over the place, then you need to evaluate what's going on. Where is the inconsistency? And of course, if we're talking about like a laser timing experiment, then you'd have to check the timing. Is it firing off correctly from the onset to when it detects again? And that sort of thing. So and again, this is just a broad example. And then the other thing that you can evaluate is your accuracy. And so this refers to how close a number is to an accepted value. And again, this only works if you have a standard value to compare it to. So that's why I was using our example of light. And so this is just kind of a visual representation of all these terms. And so if we look at A, our data set for A for our little target practice. So we can see that this is precise. So they're all kind of clumped around. And so, you know, if you're throwing it, that at least means you're fairly consistent with how you throw, even if it's kind of off target. If we look at C, so C would also be considered precise since they're clumped together. And then if we're looking, you know, at B and D, so then we can say, right, B is not very precise, so it's at least kind of more accurate. You know, it's closer to the target, but it kind of lacks that precision. And again, kind of going all over the place. So now, if this was, I mean, it doesn't really work that well with darts, but you have to think of your setup. You know, why are my numbers all over the place? I'm a little high, I'm a little low. How can I get rid of whatever variable is leading to this? And sometimes with analytical chemistry, it's like going back, making sure your standards are done correctly, that you have a nice line fit to compare everything to, that sort of thing. And then so D, right, these values don't look really good at all because they're not precise or accurate. And so with D, if you're getting results like that all over the place, then you really need to evaluate, you know, what am I doing with my experiment? Maybe it's even too complicated and I'm trying to account for too many variables. And so it's always, that's always a hard part of science, is planning a good experiment. How am I really going to prove what I'm trying to prove? And that's always the bias of science too. It's like you as a scientist want to be successful, so you have to make sure that you don't get too excited with your own personal bias of like, yes, I want this to work, and then the data I think that I'm getting, I think that it shows it, but you have to be really, really careful. I'll try to give some more specific examples as we go along. And so percent error, and so you'll actually do this in lab, so some of you did it on Tuesday, some of you will do it today in our little popcorn analysis. So then you'll do a percent error calculation, and you'll find on the lab that they say that 13.5% is the ideal water content for popcorn for a kernel. And then so you would set up your value, average value minus true value over the true value. So again, in our experimental case, 13.5. If we were looking at light, right, we would use that true value of the speed of light, and then just multiply it by 100, gives you your percent error. And just star that. So pretty simple, but commonly used formula. And so now let's go back, and the last sort of thing, and again, it'll come up in lab today, so you get to practice, is so now that we know how to identify sig figs, and we can always go back and review if we need, how do we do the math with them? And well, let's just read these rules and then we'll look at the examples. So multiplication and division, they're the most simplest to keep track of. So all it is the least precise measurement determines the number of sig figs. So you just do your multiplication, division, then you look, okay, which one had the least number of sig figs, obviously not including your conversion factors, and then you report it to that amount. With addition and subtraction, it's only a little trickier in that I feel like you have to kind of keep track of it in what I call elementary school addition mode, where you got to line them up, you know, one on top of the other. And the only reason why I suggest that is because you can only report to the value with the smallest decimal measurements. So if you only have a number that goes one after the decimal point, that's all you can go to, is one after. If you have no numbers after the decimal point, you can't report any. And so we'll look at those examples. All right, so let me pull out my calculator so we can punch along. So this first scenario, and this is again, so when you're in lab, when you weigh stuff, when you measure stuff, you always want to make sure you're giving yourself enough sig figs and you're reporting all the digits, so record every number on that balance. When you measure your ruler, make sure you guesstimate one after than what's marked, so you have your sig figs. Or else you end up like this poor scenario. So, looks like some measurement in lab was made, and they did 3.56 times 4. So, right, only one sig fig. And so you punch that into your calculator, it spits out 14.24, but this is only one sig fig, so we have to round this to one sig fig. So that just gives us to 10 centimeters squared after rounding. Yeah.
So if you had put 4.00 centimeters, then we could have reported all three.
Yeah, then we,
figs?
so, and I'll write that out for clarity. So if we had done this, we would have 3 sig figs, and then, yeah, we could do 14.2. And then we would need, you know, another digit here and 4.000 to get that 4 sig figs. So you can already see like how measurements are really important. And let's not forget our units. And then, so let's do this next example. So now we have 2.050 milliliters times 5.0. So of course it spits out 10.25. We only have 2 sig figs from our 5.0. This is 4, but that doesn't really help us. So this is our smallest amount, so we have to round this to 2. And then what's kind of the awkward thing about rounding 10 to 2 sig figs? Yeah, so we have to do something to indicate that that 0 is a sig fig. So we could either write it like that with the decimal point after to show, yes, that 0 is significant, I want to indicate that. Or we can write it in scientific notation, so 1.0 times 10 to the 1 milliliters squared. And so that at least kind of helps make it a little clearer that, yes, that 0 is significant. And then, so looking at division, so same thing applies. Don't cut yourself short on those digits. So 45 divided by 9, so it spits out 5. But then we only have 1 sig fig from our 9, so we can only report to 5 centimeters. Now this problem, so we start with 4.5. So this is 2 sig figs. And then now notice, so this is a conversion factor, so that doesn't count. This is also a conversion factor. This is a conversion factor. And so this means that only this number indicates how many sig figs we need to report to. And so it's 2. And let's plug this in just so we can all see. So 4.5 times 12 times 2.54 divided by 100. So then we get that number in our calculator, and then of course we have to round it to sig figs, so we round up to 1.4 meters. Yeah?
So conversion factors never contribute to the sig figs.
Yeah, exactly, yeah. So same thing, like if you're doing like a dozen, a mole, all that, none of that counts for the sig figs. You just refer back to that original number. And then, so now let's look at our addition and subtraction examples. And so here it is in kind of the, what I like to say again, elementary school method. You line them up. And so now I can see, okay, we're adding. So 7, 7, 6, 6, 3, 3. But now we can only go to 2 after. So now we have to round to 336.68. And then if we look at this next example, so now we get what I like to call a little bit awkward scenario here. So we have 457, nothing after the decimal place. So you can punch this into your calculator or do some math. So we get that number. except we can't report to any after the decimal point, so now we just round to the nearest whole number, so 456 centimeters.
Sorry for all the questions. If that had been 457.00, so if they had put 2 significants behind the decimal, would we report the decimal?
Yeah, then we would, and I'll write it out. So then we could report it, and these are good questions. And so now if they had given us all those decimal points, then yes, we would be able to leave that as such. And of course, just to clarify, so if they had just one decimal after, right, minus 0.68, then we would round to the 10th place, giving us 456.3. So it all just depends, again, on that least amount after the decimal point. Okay. Any other questions on the math for now? All right, we're going to move ahead to chapter 2. We'll probably go back and do review during recitation. Let's start with chapter 2. We got to get moving. So we'll start chapter 2 today, and then we'll finish up next week. So if you look at the syllabus, it kind of continues on. So we said that matter is composed of particles. And so, for example, these subatomic particles, such as neutrons, protons, and electrons, make up elemental atoms and molecules, and they're composed of elemental atoms. And so, for example, if we're looking at a molecule, so notice again it has individual atoms, so it has 1 oxygen atom and 2 hydrogen atoms, and of course you can find oxygen and hydrogen on your handy-dandy periodic table. And so how the particles come together dictates the physical properties of matter, and it's also the electrons too, so we'll really look at it's the action of the electrons that really drives everything. And so like we said, matter is defined as anything that has mass and occupies space, and so chemistry seeks to understand that. So again, a very all-encompassing field. So again, these atoms are our basic submicroscopic particles that constitute the fundamental building blocks of ordinary matter. And so these are also going to be known as your elements, right? So they're on your periodic table. So anything that is an atom should also be on your periodic table. And then, so that means that molecules are just substances formed when 2 or more, let's add different or distinct. Oh, let's do different. And I'll clarify what I mean. Different atoms come together in a specific geometric arrangement. And atoms and molecules determine how matter behaves. And so this is really the beauty of chemistry. You know, you'll start to understand not only how they come together, you'll be able to predict their geometry. From their geometry, you can predict their reactivity, all based on the number of electrons. And you can really start to see how the world works. And so an element is a substance that cannot be chemically broken down into simpler substances. So again, this is going to be your atom. It's going to be on the periodic table. That's how you know it's an element. And so again, these are our basic building blocks of matter. And again, it's a single type of atom. So a helium atom, an argon atom, you know, a strontium atom, iron, anything on the periodic table. And then a compound is composed of 2 or more elements in fixed, definite proportions. And that's also kind of the key point. There has to be some formula, like H2O, CO2. All those are defined formulas. So let's take at least a quick overall tour for a second. And so we have our periodic table. You can start to just roughly start orienting yourself with it. We'll probably take several tours of the periodic table. So notice On the left side, they're more metal in nature, so we have our alkali metals, alkali earth metals, transition metals. And then, so let's kind of point out this stair step here. So our stair step, these are going to be our semi-metals, or also metalloids. And so these are distinct in that they kind of have properties of both metals and non-metals. So if you look at the actual elements that I highlighted, so silicon, germanium, arsenic, so some of these are used in like semiconductors and computer chips for their cool properties. And we have, so other metals over here. So this is also our dividing point from kind of our metals and our non-metals. And so now once we cross over to this side, these are considered now more of our non-metals. And so carbon, we mentioned that that's like a black powder. So nitrogen, that's a gas. Oxygen's a gas. Phosphorus is a powder. Selenium. So all these are more the non-metals. And then, so fluorine's a gas. Chlorine is a gas. Bromine's a liquid. And iodine's a solid. And then, of course, these at the end are all our noble gases. And so now let's go back to what I was saying, that it has to be two distinct elements. So we have these special diatomics, and they are still considered elements. So does anyone know the diatomics? Oxygen, hydrogen, I like those. Other ones? Fluorine. There's 7 of them.
Is it like that L shape?
Yeah, the L shape. So let's highlight it. So it's the L shape plus hydrogen over here. I need to get a highlighter. So we have our diatomics: nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So you can circle those. And then the last one is hydrogen. So yeah, like you said, they make that nice little 7 pattern there so you don't forget. And then the key point about these diatomics, why we're looking at them, is that these are what they exist in their elemental form. So we just finished saying that, oh, atoms are individual molecules, but we'll dive into why later, and we'll look at the MO diagrams of these and really understand why they have to be diatomics. But for now, we'll just kind of accept they can't exist by itself, and so it's going to pair up with another atom of itself, and this is in the elemental form. So now I'll write them all down. So nitrogen, chlorine, bromine, iodine, and so that is all 7. Oh, sorry. And then does anybody know what allotropes are? Or maybe an example of an allotrope? Carbon is a good example of an element with a bunch of allotropes. Hint, hint. That's different, so we'll save isotopes for later in this chapter. Allotropes, yeah.
Is there something that forms like multiple structures?
Yeah, so I like that. So I'll just redefine it. So different geometrical arrangements of the same atom. And so can we name some examples? I was given hints with carbon. Can you name some allotropes of carbon? I'm sure you can. Yeah. So carbon has a bunch of allotropes. So diamond, you might be writing with another one. What are? Yeah, either that or it's just like charred carbon. So that would just be more like carbon in the powder form, but still good. Pencil lead, so graphite. And we name other allotropes. Ah, yeah, my old notes that I've kind of screwed up a little. So yes, buckyball. So buckyball, otherwise known as C60, that is another allotrope. So let me pull over the Wikipedia page. Good old Wikipedia. And so now this gives us a better visual idea of what an allotrope is. So here's diamond in A. And so again, these are all just carbon atoms. And so why diamond is so strong is it's in this repeating tetrahedral format. And so you can see that. So B is graphite. And so you can see that the reason why your pencil lead works is graphite, while it's really strong bonds going this way, they're really weak sheets. So they just kind of shear off in little sheet layers to write. And then, so D is a buckyball, so it looks just like a soccer ball, the same kind of geometric patterns. That's your buckyball. And then there are a couple of other ones it has on here. But then I would also add, so we have these carbon nanotubes. So this was another famous allotrope of carbon. So once they made the buckyball, they later discovered that they could also make it in like a 3D elongated tube shape, and they can just kind of grow these carbon nanotubes.
Do those occur naturally, or is that wholly synthesized by humans?
So it depends. So I believe so diamond occurs naturally, right? B occurs naturally, but then D is synthetic, so they made buckyball in a lab, and same thing with the carbon nanotubes. Those are also synthesized in a lab. And the other ones that Wikipedia lists, I'm not quite sure, but I would imagine these two are also synthetic. And then G is just the amorphous carbon, so you mentioned burning it. So anytime you just have a black pile of carbon, that's just amorphous carbon. So they also use a carbon in like those face cleaners, you know, when it says like charcoal. That's basically what it is, just activated carbon.
Is carbon fiber one, or is that different?
Let's look. I think carbon fiber is different. Let's look up.
I don't know if that's.
But I'm actually not sure. So I'm not sure if it would be considered necessarily an allotrope, but it is mainly carbon. So I'm not quite sure how they make it, but I think it has other things in there to weave it in and make it fibrous.
Yeah, and so that, once you weave other stuff into it, it's no longer.
Yeah, well here it is. It tells you actually the synthesis. So apparently it's graphite, which I had no idea, and they kind of make it into different sheets. So, yeah, not a true allotrope, but very highly carbon-based. That's cool. And then, so let's list some other elements. And so if you're ever asked to classify these, right, know that these are still elements. So that's also the other point here. So this is still an element. because it's one type of atom, even though they're all diatomic. And then these allotropes, right, these are also still all elements, even though, again, they're complex structures now, but still just one type of atom, so still considered an element. And then other kind of examples of other allotropes are going to be phosphorus. And let's go back to Wikipedia, because they have nice visuals. Oh, come on. There we go. And so some of you may be familiar with some of the allotropes of phosphorus. So you have, right, white phosphorus, red phosphorus. So those have been used, right, in war. And again, different structures. So you have white phosphorus, so that's probably more stable. Or, sorry, this is unstable. And you have red phosphorus, so you can, of course, heat it, convert it to white phosphorus. And again, different allotropes, different arrangements. You can see the structures. Then there's also a violet phosphorus. So again, you can see the structure. And black phosphorus, again, different structure, all made out of phosphorus. So you might see phosphorus. You might also see like P4. So red, white, violet, etc. So all those, again, are just elements. And then another example that sometimes throws people for a loop is S8. And so sulfur in its elemental form is actually a ring structure. We look at sulfur. And so there's its 3D structure, so it's in that 8-membered ring just like that. Again, that's going to be its elemental form. So still an element, even though it's S8. And so we can also classify matter on its state. And this is also really important when we're writing our chemical reactions. It's important to indicate like what state the whatever you're adding in is in, because sometimes, like chlorine, for example, that's one that you can either add it as a gas or you could kind of condense it as a liquid, and so that would matter. You know, same thing with other things. You could like bubble either a gas through or add it in as a liquid in your reaction, and so you just want to indicate what state it's in. And so we're just going to be focusing solid, liquid, gas, basic states of matter. And so this is probably a recap for most of you. But so solid, if we look at this at the atomic level, particles are tightly packed in and fixed in place. And so they're still vibrating, there's still molecular motion, there's still electrons moving around the atom, but right, they're still solid. You can't really move this table, can't move it around. And so once you start giving energy to the substance, so let's say this is ice, right? You start with your solid block of ice, you take it out of your freezer, you start heating it up, and now those particles, they're still closely packed together, but now they can kind of slide past one another. And of course, you know, right, you can take liquid, pour it out from one container to the next, and it always takes the shape of whatever container it's in. And then we have gas. So now gas, particles are widely spaced, maybe even no intermolecular interaction between them. So they're just floating around. And so we can say that gases, we also have a term that gases are compressible. So that means no fixed volume, no fixed shape. So of course, you could have, like, let's say those liquid nitrogen tanks. You take nitrogen, compress it all the way down to a liquid. Now it's in a big liquid nitrogen tank, and then you can release it back out to fill up your tire or whatever you need to do with your gas. And so just our recap here, our solid matter, they're fixed closely. And so again, I would say that a solid has a fixed volume and a fixed shape. So we can't change our solid, right? It's not going to be compressed, not going to change the volume. And so ice, aluminum, diamond, we can go on and name a lot of examples. So liquids. So we know that liquids have a fixed volume, right? You're not going to take your cup of coffee in the morning and try to shove it in a smaller container than what it came out of. But we know that it can just take the shape then of whatever container, so your funky shaped glass, or go through your straw. So there's liquids distinction. And again, we say that liquids have the ability to flow, and that's just from them sliding past one another. So they have just enough energy to slide past. And so you're familiar with water, alcohol, so this could be rubbing alcohol or ethanol or isopropanol, gasoline, so you're familiar with gasoline, that's a liquid. And so gaseous, like we said, now we have no fixed shape, no volume, and they are compressible. So again, a solid, not compressible, you could try, can't really do anything with it. But gases, they will expand to fill whatever container they are given, or you could also compress them. And so we can also, we want to be able to classify matter. And this is also just important when we're thinking about, you know, what we're doing. We have an experiment, then we get some sort of mixture out of it generally. And then how are we going to separate this mixture? What is it made out of? So those are all things we want to be thinking about. And so when analyzing any type of matter, the first thing we ask is it one type of particle? And so if we say no, then it's a mixture. And so let's just define a mixture as either two or more elements or compounds so this can be as simple as salt water. So you have H2O, that's one compound, that's your pure compound, plus sodium chloride, there's your other compound. Now they're together, now they're a mixture. So if you're looking at a mixture, the next thing you want to ask is it uniform throughout? And I always like to think of things in terms of food, but I always kind of think, is the first bite the same as the last bite? And if the answer is yes, then it's homogeneous. I'll just add, right, first bite, same as last. And so they have a nice cup of tea here as their example. So even if you put some sugar in there, stir it around, so it should be homogeneous and evenly distributed throughout. So what are some other homogeneous mixture examples we could think of?
Milk.
So coffee, let's say with milk even, or without milk.
Solid water.
So salt water,
Honey maybe?
what'd you say?
Honey?
Honey? Yeah, I think honey works. Actually, I don't know what honey's made out of. I'm sure it's like sugar and I don't know. What else do we have? Soda,
Alcohol?
alcohol. And I assume you mean like ones that you would consume.
Any, yeah. Specifically alcohol.
I'll put your alcohol,
I mean, I
like,
suppose you could drink the other one, but alcohol.
well, yeah, you actually can drink.
You could drink a decent amount of it. And then there was hand sanitizer that was made by New York in COVID that was 70% alcohol because it's made in prison, so people were just drinking it.
Yeah. Well, there's like a story of So if you want to purchase ethanol, as a scientist, now it's actually a regulated substance because apparently some scientists had too much fun with the pure 100% ethanol. So yeah. Everyone's a drug addict, what can I say? Anyways, so yeah, any sort of alcoholic beverage for consumption, if we're talking about pure ethanol, that's a compound. But yeah, beer, alcohol, wine, whatever. Other examples, probably go on for a while, but those look good. So then let's go back to, well, what if the first bite is not the same as the last? And so if it's not uniform, we would say we have a heterogeneous mixture. You may also hear this term, if you're talking about like catalysis, there's a difference between homogeneous and heterogeneous catalysis. So heterogeneous means you have like two different mediums. So like a gas being passed over like a solid, that's heterogeneous. So they're just two different forms. And so they have, now you kind of have to be careful with sand because sand can confuse people. But the way I'm thinking about this little picture here is like you scoop up a mixture of sandy salt water and then it kind of separates out, right? So at the top you got maybe some sand particles still floating around, but it's mainly salt water. And then at the bottom you have all the heavier pieces of sand sink down. So then that would be a heterogeneous mixture, right? All sorts of different regions with clear and more dense regions. So what else could be heterogeneous? Sangria. Yeah, with the fruit in there so everybody knows.
Would
So,
like oil and vinegar?
yeah, we could do that. Oil, vinegar, although they don't really make a good mixture since they do separate. But yeah, so that would be not homogeneous or like salad dressing.
So like cooking, so putting stuff, the bowls together when you got like mixing stuff together. Is that also, or no, it's different because that's adding stuff together.
Yeah, but it'd be like the same sort of thing. Like if you want to do like a salad or stir fry, like all those would be good.
Yeah, just anything that's got a food that has a topping.
And now we're all going to be hungry. So salad, stir fry, pizza, right? All those, unless it's like a homogeneous, maybe cheese pizza with no crust or something. But, right, otherwise you got your different toppings, your different bites. I'll also add in there like Java chip frap if we're on the coffee. So that would be like not homogeneous. You got your chocolate chips in there. I feel pretty good about that. And then, so now going back to our top up here. So now we have, if it is one type of particle, it's a pure substance. But really, a pure substance can either only be an element or a compound. And this kind of makes it easy because then you're either looking for something on the periodic table or something with a defined chemical formula. And so again, compound, I would add to here, defined chemical formula. And so this is distinct, for example, gosh, you can tell I'm such a drug addict, I can only think of drugs. Yeah, it's like, it's chemistry, it's like all you talk about is drugs and everything. Also, if you want to learn how to make drugs, be a chemist, you can make anything. Just don't like go and tell airport security that you know how to make drugs. People get freaked out for some reason. Chemistry scares people. Anyways, so what I was going with, so like with our pure compound formula thing. So let's say, right, THC, so that has a defined chemical formula. And I'll write it out just for fun. So C21, H30, O2. And then I always kind of think about like those, Are you guys familiar with dabs?
Yep.
Yeah, so you know, that's like the refined THC, but then the dab itself, right, is going to be a homogeneous mixture since it has THC in there, and then it also has all those terpenes, so there's limonene or pinene, and you can go on and on with the different terpenes, and that's what gives it the flavor profile. But that's, again, the distinction, how you can tell what's a mixture, what's a compound. So like the THC drug itself, right, that's a compound. The terpene itself, so every terpene, so you'd have to, you could separate these out. So limonene. And then, so same thing with other drugs. So aspirin, and you would have to be careful if you were trying to categorize them, because some aspirin pills will be like just aspirin, and some may be cut with like something else. So you would have to read, you know, is there filler in there? So if there's filler, right now you have a mixture. If there's no filler, then it's just a pure, you know, drug compound. Other examples of compounds? LSD. You know, LSD is really hard to synthesize, by the way. Like, you know, if you say you can make meth, that's no big deal. Like, there are so many routes to make meth. Like, but LSD, no, that has, I think it has 4 distinct stereo centers, so that's what makes it really hard to synthesize. And each stereo center has to be done under like specific lighting conditions. So it's actually like, if you can do pure LSD, like, you're a good chemist. Other examples? So salt, so like table salt. So I'll put sodium chloride, because salt could be really generic. We'll talk about salt. So barium chloride, if we want to list other salts, and of course I could go on. And then, so that leaves us with the pure elements. And so I think we can guess who's left. So again, anything on the periodic table, our atoms, our diatomics, all those allotropes, all those are still elements. Any questions about this so far? Seem relatively straightforward, at least.
So heterogeneous mixtures are different types of particles, but compounds are the same types? Like,
So compound,
but for compounds, you're mixing different elements. I'm just a little lost.
so compounds have different elements in there, but it's distinct in that it's still a defined chemical formula, and it's also just like one type of molecule. So like anything you list there, so we can look up like aspirin, right? That's a defined chemical. You can look it up. It has a formula. What other things? And even simple molecules are compounds, right? CO2, carbon monoxide. So all those are compounds. And then heterogeneous, right? It's just 2 or more elements or compounds, just kind of mixed non-uniformly. So we were thinking it could even be going back to dabs. I don't know why I have dabs on the brain. What I wanted to point out is, you know, because I was saying they're homogeneous if it's like a pure sauce, but then sometimes you can get like crystals forming if you have higher purity stuff. If you were to have like crystals and then like the sauce, as they call it, or whatever. So that would be heterogeneous, right? You have crystals forming, some crystals not forming, and so there's kind of the distinction. Does that make sense with heterogeneous?
So like the little experiment that you do in 2nd grade science where you dissolve sugar in water and then you drop the string and it forms crystals, how would you describe that in terms of, that would be uniform, right? Because it's all the same, it's just different forms.
Yeah, well, technically, so you start and you'll make a homogeneous, supersaturated solution. So that's the key when making like rock candy. It has to be supersaturated, right? You get it hot, boiling. So it's homogeneous, but then once it starts coming out and you actually have crystallized the rock salt, onto your string, then I would probably consider that more, I mean, it depends what you're defining it is. Like, are you looking at the whole system now of the glass and the solid? And in case that system is heterogeneous, right? If there's still liquid floating around, but you're solidifying, sugar on your string, but then, once you pull it out and you're just looking at just the sugar itself, then that sugar is now back to being a compound. You could argue it's a mixture if you added in, some food coloring or some flavors, so now that's technically a mixture again. So kind of see that distinction.
But that would still be homogeneous, even like the candy portion of it would still be homogeneous?
Yeah,
Okay.
yeah.
Cool, thanks.
What if you're just looking at like the candy portion? Yeah. All right, so that's just recap. So blah, blah, blah. And then, so again, the important thing of chemistry is how do we separate things. This is probably the simplest way to separate something. So you can think of this just separating, salt from water. So you could start with salt water. I would never use an open flame source like this, but you'd want some other heat. So heat that up. It leaves the salt behind. Water would get heated, then it cools down, recondenses down here, and then you would have, pure water or whatever you were distilling. So you can, distill really anything you wanted to. So if you're purifying like ethanol, for example, or trying to make your own alcohol you would want to distill. You could even distill, are you aware that like mercury is a liquid? Yeah, so you could distill mercury if you needed to repurify it, so you can distill anything. But then if you continue on in your chemical career, you'll learn there's all sorts of other separation techniques. So chromatography is just in general, a big one. So this would be used for like organic chemistry. So anytime they're doing synthesis, those poor people are running columns every day to get pure product. And that's basic. Have you ever done like the marker experiment where you put a marker dotted on like a coffee filter, run ethanol through or some sort of alcohol, and you see it separate? I saw some nods. So yeah, same concept with chromatography, and we'll do chromatography in the course of this series with TLC plates. You'll kind of see what that looks like. But then even just different, extractions and separations. So since I've talked way too much about marijuana today, we can continue on that train. So they do like CO2 extractions, and so they take carbon dioxide, put it in liquid form, so it extracts out all the goodies. And then it's actually a really sexy technique because you don't have to worry about evaporating off the solvent since your solvent is a gas. So very clean that they use that. So in organic chemistry, we do a lot of the same type of thought with that, except we might be extracting with ether or DCM or some sort of other organic to get out what you wanted. You can also do with that, you do these aqueous extractions. So you kind of put whatever salt ends up in your junk unless you wanted to make a salt. In that case, that's another kind of technique. Crash out a salt, get out a solid, separate it. So we'll add like filtrations. And so crystallizing, if you can selectively crystallize anything out. Oh, can't spell today. Can't spell and talk. I can't really spell, so. Feel free to correct my spelling at any time. And then another time where you might use a distillation, well, you wouldn't do it, but it's commonly used on an industrial scale, is separating out your crude oil. And there they have a much more refined system where each level kind of corresponds to different boiling points. So up at the top, you're going to have your low boiling volatiles, so any gases and lighter hydrocarbons will go to the top, and then like your kerosene, crude oil will be at the bottom. So heaviest hydrocarbons. And so that's how they refine everything. So just a complex system of this simple distillation.
Why would using an open flame be a bad idea?
Oh, just the hazard. You don't want an open flame, especially what tends to happen like at these joints in real life is sometimes you get leakage, and anytime you have an open flame and a potential like ethanol, especially ether, that just lights up. Yeah. Try to avoid open flames, although your first lab is an open flame, so.
So what would you use instead, like
They have these things called heating mantles, and those are kind of the safest. They have a little thermocouple in there, and they're temperature regulated. But you could also use like an oil bath. That's what I like. Sand baths, they're okay. They're just, it's hard to keep a nice even temperature gradient with sand, so. All right, so let's at least start on the conservation of mass. And so this is, again, it's easy to look back now and be like, yes, this is the way things are and this makes sense, but this was something that early scientists really had to discover, especially with combustion, like where does the material go, how do we quantify that? So that was a really cool process. And so the law of conservation of mass states that in a chemical reaction, matter is neither created nor destroyed. And so we'll learn that really chemical reactions are just rearrangements of atoms. And so for instance, if you were to synthesize sodium chloride from sodium and chlorine gas, which I would not recommend, but you could do it. So you have your solid sodium and then mix it with your chlorine gas, and notice they would just rearrange to form our crystal lattice structure of sodium chloride. Of course, completely safe now to eat. And so when a chemical reaction occurs, the total mass of the substances involved in the reaction does not change. So this is also really key. So we could also do kind of mass balancing with our reactions. And so looking at this, if we started with 7.7 grams of sodium, 11.9 grams of chlorine gas, that gives us a total mass of 19.6 grams. And so that means we should have 19.6 grams of product at the end. And so again, this is consistent that matter is composed of these small indestructible particles called atoms, and that they're just going to get rearranged into a different form. And so the next key, and again, this was part of the early trials of chemistry, is so this law of definite proportions. And for a while they were pretty perplexed by, because you have carbon monoxide and carbon dioxide. But in these early days, they didn't know that there were two distinct gases. But part of their experiments where they kept reacting, what would it be? And they kept reacting or combusting things in different ratios, so they're burning carbon with different amounts of oxygen, trying to limit the oxygen. And so they were kind of seeing that there's different ratios of products. And so this kind of led to this law of definite proportions. And they said all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. And this kind of goes back to what we said, right? Define chemical formula, but at the time, you know, they're still trying to get to that. But the other key is these are also going to be whole number ratios. And So we'll see that in our formula, but let's look at how they approach this. And so we have 2 samples of carbon dioxide decomposed into their constituent elements. So one sample produces 25.6 grams of oxygen and 9.6 grams of carbon, and the other produces 21.6 grams of oxygen and 8.1 grams of carbon. And it shows that these examples are consistent. So let's do it by mass percent first. And so if we wanted to do mass percent, all this means is we need to find the total mass for each one, and then we'll see what percent of that is oxygen, 1% is carbon. So for our first experiment, so they say that we took 25.6 grams and 9.6 grams of carbon. So let's see what our total mass would be. And so we can report to 1 after, so 35.2 grams for our total. And so now we can find our mass percent. So if we want to do mass percent, so by carbon, we put our carbon mass over our total. So now 9.6 over our 35.2. And so that gives you about 27.3%. And so let's do that for oxygen. So mass percent oxygen, so 25.6 over 35.2. And so that gives us 72.7%. And so now let's compare that to experiment number 2. So then it says our second experiment produces 21.6 grams of oxygen and 18.1 grams of carbon. So now repeat those steps. So let's get our total mass. So 21.6 plus 8.1, so 29.7. Now do the percentages for each one. So carbon again, so 8.1 now divided by our 29.7, and let's see if this is consistent. And so that gives us the same answer. That's what we were expecting. So 27.3. So we can go ahead. Let's just do 21.6, even though it should be the same from our addition. So yep, just like we expect, percent oxygen is the same. So that's one way to prove it. We could also compare the ratio of oxygen to carbon. So let's do that real quick. So now, again, going back to experiment 1. So compare our ratio of oxygen to carbon. So let's do 25.6 now, just divided by 9.6. So oxygen to carbon. And so that's 2.66 repeating, so 2.67 roughly, versus our second experiment. So let's divide it again. So 21.6 divided by 8.1. And so that also gives us the same number. So 21. And so this is again what the early chemists found. So they're trying to understand these compounds and at least see that they're in consistent ratios. So they still haven't quite nailed down the whole concept. So that was 21.6, sorry, trying to write it out. Divided by 8.1. Right, so same answer. We verified that carbon dioxide then always has a consistent formula, so it always is going to have the same composition. So that's really what we've shown here. I haven't shown a formula yet, but. And so now we get to Dalton and his law of multiple proportions. And so like we were saying, we have two elements, we can call them A and B. They can form two different compounds. And the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. And so, you know, they still hadn't quite figured out everything yet, but they're at least seeing, well, we can't have, you know, half molecules or just weird partials. Everything's kind of discrete. So that must mean that there's, you know, 2 distinct particles coming together or 3 distinct particles coming together. So they're still trying to nail down the definition in an atom at this point, but they're at least seeing we have things in defined whole number ratios. And so again, right, the confusion comes from CO, CO2. There's also a lot of like nitrogen compounds that have very similar formulas. But again, as long as it's just whole number ratios. And so now we're kind of seeing that carbon monoxide and carbon dioxide are 2 compounds composed of the same 2 elements, carbon and oxygen. They're just in different ratios. So we find that the mass of oxygen that combines with 1 gram of carbon is 2.67 grams. Meanwhile, for carbon monoxide, you have 1.33 grams for every 1 gram of carbon. And so the ratio of these 2 masses is itself a whole number. We still get back to a whole number. So now let's also look at these subatomic particles. And so we kind of mentioned that atoms are made out of protons, neutrons, and electrons. And so just a quick overview. So remember our atom, and in the center is going to be the nucleus. And so in the nucleus, that is where the proton and the neutron are found. And then meanwhile, in this little electron cloud are going to be all your electrons floating around. And so now if we look at this, and so we see, so most of the mass comes from your proton and your neutron, and you can see that clearly from here. So a proton and a neutron are both 1.67 times 10 to the negative 27 kilograms, while an electron is 0.00091 times 10 to the negative 27. So it's negligible. We don't really count it. And I think this came up on Tuesday where somebody mentioned AMU. And so this is where AMU shows up. It's when you're talking about individual atoms. So that's atomic mass unit. And we roughly say that a proton is equal to 1 AMU, so you don't need to worry about the ending 727 over here, and a neutron is also 1 AMU. So we just assume they're both 1 AMU, and we'll see that again this gives rise to our kind of total mass. Then if we look at our charges, so our charges, our proton formally has a +1 charge, and that's compared to the electron, which formally has a negative charge then, and the neutron was elusive for a while since it has no charge. And then the charge in coulombs is equal to 1.6 times 10 to the negative 19. And so this would be important if you wanted to calculate how many electrons you had or the charge. And so this is just kind of where we're going, and that we'll see these molecules, how they form, why they're in these geometries, and how these geometries affect reactivity. All right, that's a good stopping point. So I will give you probably a 10-minute break, and we'll come back for recitation. And then we should also have a fun demo, so don't leave recitation. But if you really want to leave, which I don't encourage, I do have the homework printed. But go ahead, take a little break, and we'll reconvene in 10 minutes. And I will stop the online recording of this. So thank you if you are watching.